You've written electrostatics. Okay. So we say that electrostatics is the study of stationary charges or slow-moving charges. Electrostatics is the study of stationary charges or slow-moving charges. It is the study of stationary charges. You can open bracket and write charges at rest or slow-moving charges. Hope I did not rush this one. Okay. So it is the study of stationary charges, open bracket, charges at rest or slow-moving charges. That is the electrostatics for you. The study of charges at rest or slow-moving charges. So if I know that I want us to look at under this electrostatics, the things that make up electrostatics. We know that yes, there are histories to it, where they tell you Thales did, Michael Faraday did, all those people did. Benjamin Franklin, all of them. But the key concept I want you to get once you are talking about electrostatics is what brings about electrostatics. You cannot talk about electrostatics without talking about charges. This is what brings about electrostatics. So if I know it, we can simply say that charges, you can define charges as, if you put it by, you can say that it is simply electric field, force over electric field intensity. But I feel the best way to define charge is simply there are ions, positively charged or negatively charged. So charges are ions, positively charged or negatively charged. The positively charged ions are slower than the negatively charged ions because the negatively charged ions are lighter. I said charges are ions, positively and negatively charged. Charges are ions, positively and negatively charged. Charges are ions, positively and negatively charged. Now I said the positive charge. The positively charged ions are lighter than the negatively charged ions because negatively charged ions are, the positively charged ions are heavier than the negatively charged ions. So the positively charged ions are slower, while these ones are faster. So this one, the negatively charged ions are fast-moving charges. So we call the negatively charged ions electrons, according to J.J. Thomson. So the positively charged ions, we call it protons, just like we did in chemistry, protons. So another thing I want us to note now is characteristics, or say properties of charges. Properties of charges. We have to do this explanation first so that we can easily start our calculation part because all these things are exam likely questions, and I've solved the parts that are very important, like all those things they tell you if you rub ebonite and fall. What do you get?
What be a negatively charged ebonite?
Okay, what if you rub plastic and fall?
Plastic
And fall.
Is to be no, to be positive.
It will be positive. Yes. So you need to note all those things, please, because if you notice them, that's where they pick small questions that are not supposed to worry you. And I've made video on it. And that's the one I made upstairs. So all those induction, contact, and the rest. So I've made video. We have the first video of this because I made it upstairs. So what properties of charge? The first property of charge is that like poles. The first property is that like poles repel, while unlike poles attract. And this can also be classified as the first law of electrostatics. This thing is properties of charge, and it is among the first law of electrostatics. So you can say properties of charges. Then when you finish writing this one, you open bracket and say first law of electrostatics, you close it. Then number two is that electric field charges creates or generates. In physics we use generates. In Bible study you can use creates. Charges generates electric field. So the reason you have electric field is because of charges. No charge, no electric field. Charges generate electric field. Number 3. Electric field originates from the positive charge. Electric field originates from the positive charge. And terminates at the negative charge. These are objective questions. They are parts. You see all those long stories. There is a part in your chemistry in the chapter 1, if you start reading, that looks very boring. Those are objective questions. Don't joke with it. They would like to pick things from there. That's why I will try my best to see that I make videos on all those boring parts. Simplify it so that you can watch it and remember to have it in your mind. So terminate at the negative charge. That's the third characteristics. Okay.
Sorry. That's when you said when you rub plastic and fall.
Yes.
Like the charge you're talking about, is it on the plastic or on the
No, see, like for example, let me use that your grass rod and silk. When you rub the two, they actually show you a repulsion. You see? So, but it is just years after that physicists now said, okay, let's classify this one as positive, classify this one as negative. Are you saying it? I'm coming to that point. So that means that whenever you have, what's it called? Glass rod with silk, what you are getting there as positive charge is not that maybe the two of them are attracted. But what they are telling you is that the repulsion you get there is a type of repulsion that shows you that each of the charges have positive charge. I don't know if it's making sense to you. Okay, ask.
No, it's not question on WhatsApp. Like, from what I read on that textbook, he said that the glass rod rub with the
with silk.
Yes, that the glass rod will transfer electron to the scale, making it positively charged. You need to lose electron, yes, making it positive. Yes.
Okay, wait. Glass will lose electron.
Yes,
the other one.
to the scale.
Yes, but did they say that they will not attract?
When you bring ebonite with the glass rod now.
That means you read it. That's what I'm saying now. Why you are bringing ebonite with glass rod is because ebonite has proved to have negative charge. Why glass rod? Anything glass rod has proved to be positive. So if you now go to those ones that you've classified as negative and bring it together, it will attract. Are you seeing it? But they will not tell you, like, see, they are not telling you that maybe when you rub that glass and silk, that the two are attracting. They are not attracting. So it is still repulsion, which we say that the true test of any charge is repulsion, not attraction. They are still repelling. But the only reason why you are putting that in, why they classify this positive, is that they have seen that there are tendencies from this one to lose electron and this one to gain electron. But it doesn't mean that they are attracting. So when you want to classify in the sense of maybe something attracting and something repelling, you have to go to where you have that silk or glass, bring it against the one we've classified as negative for us to get attraction. That's the point I'm trying to make. So that place we have grass rod and silk. That's not where you look for attraction. That place we have ebonite and fall. That's not where you look for attraction. What the two are showing you are characteristics. These are showing characteristics of positive. These are showing characteristics of negative. But if you look for attraction, it's not to bring any of them together. So, but I will still get to that because we are still here. Let's not be too fast so that we don't jump. Now, number four, and the last one is that the force on an electric field, is given by a mathematical expression which is F equals to QE. The force on an electric field is given is given by F equals to QE. That is due to its electrostatic force of attraction. So you can say the force on an electric field, or you say force. Yes, the force on an electric field is given by F equals to QE due to its force of electrostatic attraction. Why the force on a body as a result of it, or the force on a body due to electric field, the force on a body due to electric field is given by NA. I normally don't give my students this particular one as a definition. I just stop at this. Reason being that if I know that this is force, naturally according to Newton, F is equal to NA, right? And this is going to be equal to QE. So this is just the definition you need. So the force on a body is equals to F equals to QE due to its electrostatic force of attraction. So you can go on to express it this way. So these are the four major properties of charges that you need to note. Then we can go on. Yes, we can go on to still talk about relationship between voltage and voltage. We'll do that when we start getting to chapter 2 part of this. So, okay, so we can easily write that from here I can have that Q is equal to F over E. Shall we? Yes. So, or I can also have that E is equal to force over Q. So it is from here that you get that definition where they tell you that electric field intensity is equal to force per unit charge. And it's from here. So all the major definitions of all these things are from here. So please, I think at this junction, what we now need to do is to enter this properly, which is laws of electrostatics. Laws of electrostatics. Laws of electrostatics. Laws of electrostatics. I'll still post video on all these things. I've already made video on it, so try and watch it. Laws of electrostatics. The first law is this one. Light poles attract. Light poles repel and say attract. Are you okay? Light poles repel, and on light poles attract. Good. Attract. Even when we did couple, this thing is like couple. That time we did couple. First semester, where we said that if they are maybe moving, how do we explain itself? I said that couples are two equal and opposite forces. Do you remember? Yes. So it's more like that couple. So once they are equal, for it to have effect, they must be opposite. So now the second one, light poles repel and the light poles attract. The second one is that the force of attraction. See what this thing means. If, for example, I have this charge here and I have this charge here, I come and put this one in the north, put this one in the south. Do you know what will happen? Whether you are existing in the east, somebody in the north don't know. Do you know? Are you aware? Yes. And whether somebody is existing in the north, you are not aware. Should you know? So the more the distance, the less force you have. But the minute you make a charge come close, what will happen? It will have like, so it's more like it is varying inversely. So if you increase distance, force will reduce. Now if you bring distance close, force will drop. So increase in distance, less force. So decrease in distance, more force. So because by the time you decrease the distance by bringing this thing close, you see that distance is not small. That means that the force of attraction will be too high. So that is just the principle. So the law, the second law states that force is inversely proportional to square of distance apart, and then directly proportional to the product of the two charges. So we can simply say that this law, this thing that we normally attribute to Coulomb, was first of all given by Faraday. But it's just like he didn't have enough proof to back it up. So it's like a Faraday that gave it. And he's the one that gave this line. This thing we normally call lines of charge. Electric field line. It's like a Faraday that gave it. So, but Coulombs is the one that perfected it. So, he said that force of attraction between two charges is directly proportional to the products of the charges and inversely proportional to the square of the distances apart. So, if I have this can be Q1, Q2. So, by the time you put it together, you see that F is equal. Once we introduce proportionality constant, K will come in. Shall we?
Yes.
So, Q1, Q2 over R square. So, and we know that I want to get the unit of K now before we. Yes, we know that K is equals to 9 times 10. Shall we? But I don't want us to guess the unit. Let's prove it. Let's find it. And K can also be the same as 1 over 4 pi. Very simple. Very simple. You see why I don't want you to be cramming it. So don't even think of cramming it. And you know that why this 5? Do you know why this 4 pi is here? Hope you know why this 4 pi is here.
From the formula.
Because of that proof that Gauss gave us that this is a point charge, and point charge forms sphere. And area of that sphere is this 4 pi that is here. Are you seeing it? So there is no need cramming it once you know it. So if that be the case, I will now have that to get K, what K is here. Let me try to make K subject of the formula. So I now have K is equals to F
R Q1, Q2.
Which is the same as Q squared.
Yes.
Okay. So that this now becomes K is equals to force is a Newton. Meter squared.
Over Coulombs.
Over Coulombs squared. Very, very sharp. And please, you need to note that once you are doing electricity, anywhere you see distance, D is a, or maybe S, anywhere you're supposed to put D or S is equals to R. Like for example, when we study electric field potential, which is voltage, you hear us say that it is defined as the work done in moving. Yes. That one is textbook. The simple definition is simply the work done in moving a charge from one point to another. That's electric field potential. So the work you do, the work that a charge does, whenever it moves from one point to the other, is electric potential. So which is the same thing as saying V equals to work done over Q. So V is now equals to Fs over Q. This S that is here is supposed to be R. That's what I mean. I see it. And we know that F over Q, we still going to prove something that F over Q is equals to something. So no rush, we'll get there. So this is now going to mean that K is equals to Newton meter square, then per square Coulomb. So that means that this is just having Newton meter square per square Coulomb. So this is the one I want you to have upstairs. So we don't have to cram it. That is for K, the unit of K. So if we've gotten to this point, the next thing is to define electric field line, because we'll make use of it to show charge. They can draw something for you, you are to show which one is positive and negative, how does it attract, how does it repel. Follow the back. Now this one is locked. So for that reason, write as a subheading electric field line. Hope we are not too fast.
No.
Okay, electric field line. And these things that we are doing, we are just repeating it to come to our memory. But it's very simple. So electric field line. After this, we can now go to the calculation aspect. Electric field line. So electric field line, we define it as an imaginary line used to show the direction of the electric field. So you imagine, okay, if positive naturally from the law, if positive is the one that it originates from, that is always giving, and negative is the one that is always receiving. If that is the case, when I have negative, when I have positive in an electric field, how do I show that this is the direction of the electric field or charge in the electric field? So we say that electric field is an imaginary line used to show the direction of the electric field. Full stop. It is an imaginary line used to show the direction of electric field. Or you can also define it as an imaginary line that shows the direction of charges in an electric field. You know that electric field, what causes it is charge. So we can say that it is an imaginary line an imaginary line that shows the direction of charges in an electric field. That is why, you see, they are divided by your textbook into chapter 1 and chapter 2 so that you'll be able to categorize. You don't feel it's too much. But normally, if you're treating this chapter 1 and chapter 2, it's almost the same thing. You see, most textbooks treating it as the same. Notice that I'm mentioning things inside the electrostatics that are taking me to chapter 2. Yes. So please, I want you to note that electric field, in simple terms, when you are defining it in your textbook, you can simply say, please write it. Electric field is a region. Electric field is a region where charges at rest or stationary or slow moving charge, you say, is a region where stationary charges or slow moving charges experience electric force. So it's not hard. It's a region where stationary charges or slow moving charges experience electric field. So that is electric field for you. That is electric field for you. But when it has to do with electric field intensity, I think electric field and electric field intensity, they are the same thing. It's just that intensity that you are seeing there is not telling you the direction or how strong the charge in electric field is moving. So electric field intensity tells you the direction or how strong the charge found in an electric field is. That's electric field intensity, or we call it electric field strength. So it's important to note it. And when you now want to get the formula of electric field intensity, it is simply from this that you get it. You make this subject of the formula. So you see that it will now give you force per unit charge. That's why sometimes we just define it as force per unit charge. So with this said, I want us to look at the questions we have in our exercises. There are calculations there that I want us to look at. You see all those ones from number 1 to like all those mount hole, like all those ones, like they say draw electrostatic field lines. Okay, let's just do it so that we do that number 6 and then start the calculation. They say draw electrostatic field lines around 2 nearby positive and negative point charges. Have you seen it? Number 6. So I know that if this is an electric field, so and I have positive charges this way.
Yeah.
Naturally, this one tends to move out. Is it not true? Yeah. This one always move out. Even this side will move out, this side will move out, this side will move out, move out, move out, out. Somebody wants to say, what of this one that you are putting here? Is it not? Notice that on this, that means that the area of electron will be this way to get the 90 degrees. So if I have this, I'm coming. Notice that for the fact that it's used to moving out, and this one is used to moving out, by the time the two hit each other, anything here you hit each other, what will happen is that this one will easily change direction. The same thing with this one, change direction. That's why you see it in the textbook, they now have it this way. To change direction. Because it's trying to enter, it's now agreeing, it's now going to be moving out. So it's a repulsion. But notice, this is when I have 2 positive charges. But on an account here, they tell me now that there is an extra negative charge. What will happen is that these 2 positive charges, yes, immediately they see negative, they have no business to come together. They just move freely to this one. So you see that this will just come here, this will just come here, everything about this will come here, even this way, and but let me just use this 2. The same thing with this. Hope you know that if I have maybe 3 lines here, and I have like 2 lines here, it means that the charge of this one is weak. So the more electric field line you have, the stronger your charge is. So I have like, let's say I have equal electric field line, that means that their strength is the same. So if I have this, it doesn't stop here if you draw it this way. You need to still go and show that on this side, let's say these charges, even as they are moving this way, there are ones that are still moving this way and they are going outside. So that if you are able to put any negative here, it will still go to it. So you always need to make sure that on each angle, then this is negative. This is negative. Don't go and be drawing all those things that you normally see. As students that has done Gauss law, you've seen the direction of charge. Don't go and be drawing all those things you see in some books drawing. Charges don't move this way. This is not the direction, the way they assume charges to be moving. So you put it this way, put it this way. This is to show that this one is on the receiving end. Very important to note. Another thing I need to make mention of. Okay, that one is under voltage. Let's stop at this one. So it's almost each time you are doing chapter 1, when you go deep into the course, your mind will be telling you enter chapter 2. They are two related. They are almost, even if you check that chapter 1 exercises, you see that most of the questions they are asking you there are chapter 2 questions. So they are two related, and that is why before I start the questions we are to solve, I want to please touch the relationship between electric field intensity and potential, electric field potential. Are you seeing it? So that we can now start solving our calculation. So I know that if this happens to the negative charge, what will happen? Let's say I have two negative charges here, what will happen?
To repair.
You know that this one moves this way, Shirley? This way, and this one. They don't even have business, but the only way to show that they are repairing now is that instead of it going this way, you now come and show that this will have this like going this way. So if there's something this way, this one goes this way. So you need to note this. So I now know that electric field intensity is what? Define electric field intensity for me.
It's the strength of the charge.
It's the strength of the charge.
In an electric field.
In an electric field. Sharp. Or you say it's the direction. Yes. Why electric field potential is the work done in moving a unit positive charge. Do you know why they normally use a unit positive charge? Because they take it that what is moving is positive charge. In reality, that is not the case. So, in a particular charge system, because electron is higher, it tends to move faster. I see it. But physicists, as of the days of because of chemistry, metals giving out, not metals receive negative. So they assume that the charge is positive. The one going out and the one entering inside, the one receiving is negative. So that's why in most cases you always see that a unit positive charge being added to the definition. Just to tell you that it is the positive that they are assuming that is moving. So I said that electric field potential is the work done in moving a unit positive charge. Electric field potential. Electric field potential represented with V is the work done in moving a charge or a unit positive charge from one point to the other. So you can see sometimes they tell you unit positive charge from infinity to that to a point. I know that there is no use for that. So a unit positive charge from one point. When I say from one point, I don't even know the points. So it's still from infinity, from one point to another. So this is V. So we simply give it by V equals to work done over charge, which is essentially saying Fs all over Q, but in electric field we don't use S, we use R. So it is simply FR over Q. And we know that F over Q from here, F over Q is what? Electric field intensity. That means that voltage is the same thing as saying ER. Very simple. So it is this thing that shows you the relationship between voltage and electric field intensity. This is the formula for the relationship. So if you now want to maybe make electric field intensity subject of the formula, you can now say divide both sides by R, so that you now have E equals to V over R. So electric field intensity, in a case where they give you voltage and radius, electric field intensity can be the same thing as saying voltage over R. Very important. And we know that we can expand all these things if we're applying Coulomb's law. Should be, you know, because the force I have in this case can mean something. If I choose to replace it. So when we start solving calculation, we'll do it. So with that said, there's a question. If you check that book, a calculation question that was given, they did not give charge.
It's going to be 1.6 times 10
1.6 times 10 is, you are using electron, you're using the charge of the electron. Should that's what you're using. That is the smallest. Reason why you're using it is that you're using the smallest unit of charge. Yes, and the smallest unit of charge is that of electron, which is the same thing with proton, just that the sign is different. You need to note it too. Please, how many microcoulomb? How many microcoulomb makes 1 coulomb? You know that the unit of charge is coulomb, right? What I said is, how many microcoulomb make 1 coulomb? I did not say how many coulomb equals to micro. I'm saying how many, that is if I have 1 coulomb, 1 coulomb is equals to how many microcoulomb? That's what I mean.
1 million.
1 million. That's what I want to hear. So 1 million microcoulomb is equals to 1 coulomb. You put minus. You are putting minus. I don't want you to cram, because that thing you are giving me is copied from textbook. It's not minus. That's why. So please write it somewhere. There was good now. Write it somewhere now. Then if they ask you how many nanocoulomb make 1 coulomb, how many nanocoulomb?
1 billion.
1 billion.
Yes.
Then if they ask you how many millicoulomb, how many millicoulomb make 1 coulomb? Do you know why I'm telling you this thing? You might see it, especially that one that is micro. They normally give it. So let's read out that question, all the calculation questions, then let's tackle it. Let's see what we can do with it. Yes, I know that as we are solving it, we will now be discovering shortcuts that we can use. Nano is NBC. Micro is like this. Let's just write it. So if I have something like this, so we say that 1 million of it is equal to 1 coulomb. Then 1 billion of the nanocoulomb is equals to 1 coulomb. They will say that 1,000 of the millicoulomb is equals to 1 coulomb. So yes. So if I have 12 is like trillion. Yeah. Shebi? So if I want to do picocoulomb, which they hardly give, I'll have like 12. 6. So I have PC. But I know that nobody will ask you this too. But for the sake of our class, we like to know it. So you can write it inside your notebook, so you don't have to punch it. So what it means is that using that our first semester trick, if they give me, for example, 15 microcoulomb, if I want to convert to coulomb, what I just need to do is to remember that 1 million of it equals to 1 coulomb. This one is equals to X coulomb. So that I now have this times X. So 1 million X is equals to 15 microcoulomb, and this one is S coulomb. So by the time you divide by 1 million, you get your answer. You remember that that's our conversion. So this one is now simple. So please let's look at the first question there. On that exercise, the exercise page, let's see if we can solve all the exercise pages fast. Then move to chapter 2 proper. But when I gave you that relationship with potential energy and electric intensity, is that there are questions from chapter 2 instead of chapter 1. Okay. If you look at the questions given here, you go to, okay, let's start from the first one. They say if two similarly charged metals are brought 1.5 meters apart in a vacuum, you've seen it? If two similarly charged metals are brought 1.5 meters apart, so I have charged metals, but they did not give me Q1 and Q2. So, I don't want to use 1 microcoulomb because that's not the smallest charge. The smallest charge is the charge of proton or electron. So, I think if you check the answer we are giving here,
They used 1.6 times 10 to 1 minus 19 and so
1.6.
times 10 to 12.
Okay, that is for electric, for proton.
Yes.
Because so help you know that this charge is the same for electron and proton. Just that if its proton is positive, if its electron is negative. Very important to note. What about the mass of electron?
9.6.
Is it 9.1?
Is it 9.6?
9.11 times 10 to the power of minus 31. Okay, kilogram.
Like this?
Yes, kilogram.
Okay, what about proton?
Is it mass of electron? It's 9.1.
9.1. Okay, that of proton come.
Proton is
1.7.
1.7.
1.7
Times
167.
10 is called minus 160.
27.
Like this?
Yes.
minus 27.
Proton. This one should be like this.
Yes.
Okay, I want us to check something. Let's say this is kg and this is kg. Between the two, which one is heavier? Or which one has more mass?
Proton.
Proton has more mass, should be?
Yes.
So that is why they are telling us that this one is heavier and this one is lighter. And that is why they tell you that even if you have a charge that they are the same thing, that the one that is negative tends to be the one moving, actually, in reality, not the one on proton, because this one is heavy, this one moves faster. So you need to note it. But when you are representing this, because it's now what we call, that is why in physics we call what we are doing here, all these arrows we show, we call it conventional. We are using it to pass a message. So that is what it used to be. So note it. So if I know this, I have Q1 and Q2 1.6 times 10 raised to the power minus 19. So please, anytime they do not give you charge, just go and notice somewhere that you should use any of this. That is for proton or for electron. But why we are using proton is because we understand that in electric field, charges originate from positive. Always remember it. I gave you properties of charges. So if I know that, I now go on to it. Then I said 1.5 meter apart. R is 1.5 meter. Then in a vacuum, okay, they say in a vacuum, that means that in a vacuum, my E naught remains 8.85
times 10 raised to the power minus 12.
and E.
That question I used
Question 2. If for the electric is 1 in a vacuum, if it's not in a vacuum, it's greater than 1. Always remember it. But there will be no use for it, or you just need to have it in mind so that as you are solving anyone that they want to throw it inside, you will not be thrown away. Now, then I said, is the force attraction or repulsion? Thank God. I hope you know that if my force, anything negative in chemistry and physics means what? Let's say, for example, if you are a non-metal, should be when you receive electron, you become negatively charged. Yes? So negative means attraction. But when you lose electron, you become positively charged. So positive means repulsion. So anything we are solving and our answer ever end up with positive for force means that the force is repulsive. But if we ever end up with negative, it means that the force is attractive. Very simple to do. So we can now solve. I think that's all. That's all. So in this kind of question, all I just need to do is employ Coulomb's law. F equals to K Q1 Q2 over R squared. So that F is equals to K is equals to 9 times 10 raised to the power 9 Newton meter square per square coulomb. So I have 9 times 10 raised to the power 9. Then Q squared, because it's just 1. So it's the same as a 1.6 times 10 raised to the power minus 19 all over. Our R is 1.5 and it's in meter, and meter is in units. So square. So punch this, let's see what you have. Punch it, let's see what you have. So we are solving question 2. Question 2 in exercise 1 under chapter 1. So punch it. So I know I've made 3 videos today. The first one I made is on everything that has to do with the objective aspects, explaining how force and all those things work. Then Gauss law. Then this one is non-calculation. So I'll just know all of it.
Gauss law.
We've done it, but we'll pause the video. Okay, so what did you get?
1.024 times 10 to the power minus 28.
1.024
Times 10 to the power minus 28.
times 10 to the power minus 20, like this.
Yes.
Check, everybody. Okay, there's no negative sign here. Okay, so if there's no negative sign, that means that the force is repulsive. That means force is repulsive. So we have a repulsive force.
Yes, sir. It's not the same answer.
Where?
He gave answer.
Background.
Follow the back door, my friend. So they give us first one. What's that first one?
Background.
Isha! Welcome. I'll come with which one? They said,
This one is just by the previous time.
if two similarly charged metals are brought 1.5 meter apart in a vacuum of dielectric, what?
Dielectric constant.
What this thing is? Which word is it?
Read what you have. Read what you have here.
But the same question.
It's the same question. Read it out here.
If two of similar charged metals are brought to 1.5 meter apart in a vacuum of dielectric constant 2.
Okay, the vacuum of dielectric constant 2.
Yes, but here just dielectric constant.
They did not give us 2 now. They did not give us 2 here now.
This one.
Okay, the one you're solving is the one you're practical one. They gave 2 there.
Yeah.
Okay, so let's say
Okay, let's put 2 here.
they put 2 down. Yeah. Wow. Okay. Okay, that means that if
Oh, yeah.
that means here, do you know what this thing means? If that is the case, remember that ER is equal to E over should we? And if we are given the electric constants, so this is ER is equal to in a vacuum this is 1. We don't know this one, should we? But they gave us this one to be 2. Is it?
Yes.
Yes. So if I make E naught subject of the formula, I will have this is 1 half
To be half.
E naught equals to half. Should it? Yes.
To be half.
So E naught
So
equals
just
to
add 2 to the 1.5.
Divided by 2. Like your answer, what you get as your answer divided by 2.
I'm
Or
coming.
now it's going to be 1 over 4 pi times 2 times 8.85 raised to the power of -12.
That's
So you say just add 2 to
Look at this thing. E is equal to E
just
power
add,
multiplied by E naught.
just
Why
wait,
this?
you just times it 1.5 squared. Just times 2. Then I mean, just add times 2. Then do it again.
Okay, we know that this is called this is hello. This one we don't have it now. Okay, but we know that this one in a vacuum is equal to 8.5, should we? Okay, see.
You know, 1 over 4 pi
And-
it is the same as 9.10 squared.
Okay, but let's check something. Let's check something, please. Look for me, E naught here is 1/2, should we? We can increase E naught. That means half here is equal to 8.85
Yes.
times 10 is minus 12. That's what it is now.
Times
No, there's no times.
Divided by
C
E.
naught also has its own constant.
Yes.
So what about the number 1B? No, sorry, number 1C.
It's simple. You got NE.
No, we didn't put the number 1C. Number 1C.
Okay. Okay. That means okay.
You made a mistake.
It's not a mistake. This is not constituted. Even if it's right, it's not the opposite. Like, that's the
Okay, see see what I'm trying to show. I'm assuming we know that E in a vacuum is equal to what, right? Let's have E here. Yes, do you know why I want to do this? You said that the dielectric constant is 2, Shelly. That is, this one now is 2. So I want to just replace this with my E.
I say it?
No, don't worry, I'm coming. Yes, now. If I make this now, if I make the subject of the formula here, because E here is the dielectric constant. This one is relative permittivity, shouldn't it? Relative permittivity. So the electric constants here is 2. Okay, that's what it's saying. So if I make the subject of the formula here, I should be having 2 E naughts. Check.
Then this thing has to show you that.
That's what you wanted to show me. We'll use it.
Then that E from what I would there from E is equal to E naught ER.
Don't worry, let's solve. If we solve it well, we should get the same thing you have. So let's check. Let's check. I know that I have over here. That means that at this point here, I solved everything here. If there's a dielectric constant, that means I'm not going to use K. I'm not going to use force to be K, Q1, Q2 over R squared. So I'm going to now make room. Okay, I've seen what you're saying. I'll make room for K, which is equal to 1 over 4 pi permittivity of free space, shall we?
Yeah, and yes.
Multiply by Q squared.
You can suppose to give you the same answer. You can suppose to use that one. Just
And
the previous So I supposed to give the same answer.
Then I now have times, I'm coming over. I'm having now Q1, Q2, all over R squared, shall we?
Yes.
Okay. Well, we have permittivity of free space now, which means if I make this subject of formula, this should be E equals to 2 over E. Is it not?
No.
Yes.
Yes.
0 over 2 or 2 over E?
You supposed to, if you do it like this, like K, Q1, Q2 over 2R squared, you're supposed to give you the same. If you do it like, you're supposed to give you the same answer.
Don't worry. Don't worry.
So it's good.
Don't worry. Do you know why? Do you know why we are confused? Because we are insisting that this thing is 0. Hello? See, calm down. Let's now do together. I've read the question over and over. Last. I've read the question over and over. That's the problem. This thing I would normally say as permittivity of free space, which is E naught. K is equal to 1 over 4 pi E.
Yes.
But it is 1 over 4 pi E naught when we are not given anything like dielectric constants. Are you saying it? Yes, because in that case where we are in a vacuum, without dielectric constants, E is 1. We are not using permittivity of free space. So for that case, when we have our dielectric constants, this E is not E naught, but actually this E. That's what was keeping us. So I will replace this E with 2 E naughts. So that I now have K is equals to 1 over 4 pi. So replace E with 2 E naught so that I now have
2 times E
naught. Is it confusing?
Yes. Or is it 2 E naught?
I'm coming. See now, see. I said earlier that when we have E. See, let's say we are not given anything like that electric constant. We know that ER is equal to E over E naught, shall we? So when we are not given anything like relative permittivity here, like in this case that we are given 2, when we are not given anything like this, yes. So we take it that this is 1 on account where we are not giving dielectric constant, we take it that this is 1. So that by the time you equate it, you see that in this case, this should be our E equals to E naught. Are you seeing it? So if we replace this now, in this case, that is where we now have this to be E naught. But on account where it is given to be 2, if we replace it, we should have 2 E naught. So these are simple things that are easy to forget. Didn't mean I forgot it. So if I do it well and I have Q1, Q2, all over 4 pi 2 E naught R squared. So simple things, easy to forget, but we are recording it. So when you are reading, you'll be able to put it together. So this is going to be K with a. So let's do it now. 1 over 4 pi is 2 over 7. 2 over 7. Then it's supposed to get 2 E naught is going to be 2 times
8.85.
yes. And then times
1.5 square.
1.5 square. Then my charge is times, this is 1 times,
The
Sir, you don't want 697.
The charge given here, that is also the mistake.
okay, they give us charge in the question.
There's no charge.
There's charge.
Blood of Jesus. Blood of Jesus. I want to see.
So you see light and electromagnetic.
You know that this one is equal to 1. This new one, they brought it out. This is so please, give me the charge again. Let's not use this charge.
697.
I want us to get something if we can get 697.6. Wow. That means I'm going to throw away this one. I'll go back to using my normal textbook. So this is not going to be 697.6 square. Punch is, let's see if we have the same answer. So try punch. Calm down and punch. Let's see what we have. Okay, is that what you have here? Like punch this one. I want us to see what you have. Do 697.6 square. 6.6 square. Then divided by everything we have. Let's see.
Yes, it's 9.7. This one is 9.73 times 10 to the power 14.
Times 10 to the power 14. Is it minus 14 or 14? 14. Okay. So please, punch and see if it's the same thing you get. Let's be sure. Good. That means, please, as much as you're not science student or medicine student, you try and get that old one. That's the one we use from anybody in upper level. That's. I know, but like to be comparing it, because if you check it, you see that it's almost the same question. It's just that they lifted some things. And it's still the same thing. The law of electricity and magnetism is the same. So punch, check if it's the same thing.
9.73 is even good.
No. What I mean is like punch this one that we have if we get the same thing. And it's going to be in Newton.
9.7201.
72.
9.7 times 10 is power 14.
Okay, 9.72. Okay, not 73.
Yeah.
What's the 3 0?
It's still now.
I know it's almost the same thing. But let's use what we got in class. Yes. So when you go, I think the approximations will make here that reduce our answer. But please, where you will get confused, I think where you will get confused is that part. So that's why you need to remember it says For the fact that you're in this class, do you know the simple thing to do? Anytime you're giving anything like dielectric constant, what you just need to do is if they are telling you that there is a dielectric constant there, just say, if they give you dielectric constant to be like 12, just go and do 12 times E naught. Let's say they gave me dielectric constant to be 12. Are you seeing it? So just do that. In that case, this is going to be 12 now. And here is 12 equals to E all over E naught. So you see that by the time you make this element of the formula, it's now going to be 12 E naught 0. This E is always, this E on its own is always what we are trying to represent when we put even this K to be equal to 4 pi E naught. Okay, ask.
When are you using that formula that K is equal to 1 over 4 pi E naught and K is equal to 1 over 4 pi E?
When we are using it is when they give us the dielectric constant.
For the one that's 4 pi E.
Once they give you, pay attention. You have to pay attention so you get the point. If they give me a question and they tell me that it is in a vacuum or whatever happens, I am assuming that E on its own is equals to 1. I'm assuming that this E is equals to 1, that ER is equals to 1, E naught is equals to 8.85 times 10 raised to the power minus 2. But on account where they don't tell me that there is a dielectric constant given to me, maybe 2 or 30 or 40, that dielectric constant is going to this. It's going to this one. If this is in a vacuum, it's going to be this one remains 1. I just say that E is on its own. But if it is not in a vacuum, E is just greater than 1. So this E here, the work of this E, what it's doing with the 1 is simply trying to show if it's in a vacuum, it's equals to 1. If it's not in a vacuum, it's greater than 1. That's what it's doing. So on account of that, I remember that ER is equals to E over E naught. So I now know that if they gave me dielectric constant to be 30, that means that this will be 30 equals to 30 E naught equals to E. Very important. So please note it. This is when it is not in a vacuum, not in a vacuum. But if it's in a vacuum, it is equals to 1. Not in a vacuum. And it's easy to forget this thing. Because once you are solving, you are getting fun to using this. So it's easy to forget it. So remember it. So let's go to the next question. Please be sure that this our answer is correct so that we always. Thank you. Then check, look at number 7. Look at question 7. They say, how far apart must 2 protons be? You've seen it, number 7 question. So we will try to solve all the calculation questions in this exercise 1. So we can have time to revise chemistry chapter 2. I posted gas laws, chapter 1 of chemistry last night. Hope you've seen it. So use it. There is no question they are asking you that is not in that particular gas law I solved, because I tried to solve as many questions as possible. Different ways that they set the exam. So let's try to solve that question 7 together. Can I claim?
No.
Remember I said that E is in a function of telling you when it is greater than 1 or equals to 1. Whatever value given to you as your dielectric constant goes to ER. You need to know its relative permittivity. So you don't forget. And this one is for the mass of electron, mass of proton. But can I clean this side?
Yes.
Can we start what we have? And one thing about physics is because of the fact that it deals with physical things, there are some things about it that you must store in memory. It's not easy, but you just have to store it. And if you notice, this your second semester physics is all about formula. anyone they're talking about, before you even start to understand the concepts, they throw formula to you. So I have my distance apart on this one. I have my charge. They say take mass of proton. Mass of proton. Number 7 is size 1. Mass of proton.
So we are not through with this one.
Yeah, I know, I'm just writing out. So be solving. Be solving it when you're done. You not tell me so we solve together. This mass of proton that they gave me, is it correct? Is it supposed to be 21 or 27? So if you notice there are slight errors in that new one. Let it not confuse us.
So was that since they made mistake in that we use the exact one also they give it.
You see your textbook, you use the correct one because I believe they omitted that particular value.
Yes.
So you use the correct one. And even in the exam when they are giving it to you, they will give you the correct thing. There's no one person that is sitting it. All these ones that you see textbook coming and they rush it. So please find someone that has the old one so that you're using the two together. Now that we've discovered that it's carrying error. Then they ask, notice that in that example question, they did not give us charge, but we ought to know something there, is it not? Check that question, they did not give us charge.
You know the charge.
Because it's proton. Exactly, because it's proton. I would say that proton is 1.6. Can you see it? Because somebody somewhere might be looking at that question and saying, which one is this one? There's no charge. You need to know it. That once they talk about proton, that's the charge of proton. So, applying our law. And notice that they did not give us any dielectric constant in that question. So, we'll solve our thing peacefully, no problem. K is equals to 9 times 10 raised to the power 9 Newton meter square and square coulomb. So that means that it's more like anytime they give you that electric constant, you need to go and pull out that K is equals to 1/4 pi E. It's even best to do it this way. You see it as a science student now, but you can always remember it. So I now have that F is equals to KQ squared all over R squared. So now that F, did they give me force?
I said it's equals to weight on the earth's surface.
Energy.
Okay, they say that it's equals to the weight on the earth's surface. Okay, if that is the case, so please, if that is the case, F now. Thank you very much. Very important. Equals to KQ squared over R squared. So because they are no longer talking just about the charge, but they are saying the effect the charge has on Earth. They want to know its weight on Earth. So I know that mass of this is 1.7 times 10 raised to the power -27. Then this is constant, 9.8. Do you remember?
Yes.
Equals to. Always look at this charge something as electric field and earth surface. Everything you have in electric field is already in the earth surface. In the earth surface you have mass. Electric field you have charge. Earth surface you have acceleration. Electric field you have electric intensity. Always look at the two as the same thing. So when the question now asks you anything that relates the two, you now know that F will now be MA equals to QE. Or if it's F equals to the normal this one, you apply this formula with the easy. This acceleration, this acceleration, gravity. I have 9 times 10. I know that this semester physics will be much better than first semester.
I swear.
Yes. Yes, this one is straightforward. This semester is very straightforward. So I have my Q, which is 1.67 times. There are some people that up till now, they don't know anything about power and work. And it's professors, but they're scaled through.
What God cannot do.
Yes, sir. R square is what we are looking for. No, R is what we
I'm
are
saving us because I like to objective.
So I need
It's still you. I'm sweating.
that's what we'll do now. We'll make ourselves a form by taking square roots. Yeah. You know, I'm making video for public too, so they need to see the step one by one. I could have done that here. But let's continue. So punch. What do you have on this end? Punch it. Let's see what you have. By the time you do 1.7 times 10 raised to the power minus 27 times 9.8.
1.67 times 10 raised to the power minus
1.67
times 10 raised to the power minus 26.
Another person confirm it to
1.66.
Times 10 raised to the power
10 raised to the power minus
26.
Okay. What you do for me? This 1.67 times 10 raised to the power minus 19 squared. Times it with 9 and times 10 raised to the power 9. You know that if you don't know how to punch calculator well, it's best to use indices.
2.304 times 10 raised to the power minus
2.304 times
10 raised to the power
minus 20, like this. Okay, all over arrow square. So that we can now make our solid of formula cross multiply so that I now have arrow square into 1.67 times 10 raised to the power minus 26 equals to 2.304 times 10 raised to the power minus 28. So divide. Do you know the secret of this semester physics is simply come across me. This semester physics, the name is come across me. Because once you come across any topic with food in your stomach, you must understand it. But if you do not come across it and you enter exam hall, it will look very strange. So that's this semester physics for you. It's very easy. It doesn't waste your time. So R square is equals what you do for me. Eh?
I got 2.5.
I got 2.5.
Minus 1 times 10 raised to the power minus 28.
Okay, you got 2.51 here.
Yeah.
Okay, 51.
0.
Okay, 2.510.
Times 10 raised to the power minus 28.
If you don't have calculator, we now have calculator for sale. Eh? So you don't go and be punching what I don't know. I've told you sell your phone and buy calculator. So you don't use phone and be punching for us. I now check. We are correct. I punch it. Let's see what you have. Punch.
503 times 0.01.
Like this. Did you take the square root of? Just do division.
Okay, square root.
Don't take square root. Just do this one together.
0.0150.
0.0.
150. What did you get?
1.5.
1.503 times 2.
1.503
times 10 raised to the power minus 4.
No, it's not correct. What the one that she says is
You
correct.
just say
What the one that she says is correct. Because that division. Wait, no, that one that she said with that division is correct. Because that division is minus.
So this is the calculator she's using. This is the best. ES plus. Let me see you. 991 MS. This one is second to the one that's similar to this one. That is, this one is third born. This is first born. There's a second born. This one is not among the one.
Go so
You have calculator. You have another one.
Yes, all the calculator types we have it
How
now.
about
Let me see that one. This one is 5,000.
5?
Yes, 5,000. That's ES plus. That ES plus is 7,000. Yes.
People.
Yeah, it's like we always go to the right place. Shabi is like this, you got it 0.0150 Shabi. No, if we want to sell anything, we make sure we go to the right place and carry it, because students, you can't carry something you're selling to students and you come and be selling it to what others are selling. So we always carry it to be very less. So please.
So start out with an example now.
Is it in this case?
When you're doing all this.
No, it will be the same. You know, the only thing is just you practicing your calculator well. It will give you the sense and not rushing. If you check it out, you see that maybe you miss something, or maybe your calculator mode, the way you set it. So as you practice, it will always work out well. So don't panic. Let's take the square root of both sides to make this solid formula.
0.1.
So r is equal to 0. Like this, 122.
Yeah.
0.12.
Like this.
Yes.
Check well.
Yes.
Are you sure?
Yes.
It's 0.12, and it's going to be what? Meter. So that will be my distance apart. That should be my distance apart. So check if there's any other thing they ask us there. It's only distance they ask for. So that means that from that question, okay. That means that from that question, they said how far apart must two protons be if the positive force acting on either charge is equal to the weight of S. So how far apart it must be is 0.12 meter. That's the answer. So let's go to question 8.
7.
So we are going with 7. Okay. The one you have 37 in your own is even two equal charge carriers.
Yes.
That's the one we are going to.
Question.
Those of you in medicine and nursing is question 8. So other department is 7 for the other departments. Okay, should we start? Okay. So please, but if you notice, what we are doing is not just that we are solving. We are trying to, Ishak, are you sure you are here? Check your notes before you arrive. We are trying to make sure that we understand the different ways of solving questions related to electrostatics. And we've seen something peculiar. That is not every time we use K equals to this. Once that electric constant is mentioned, there's something we need to change. So this one that I'm seeing, the next one, I see that there's something like acceleration there. I see that there's acceleration there. I see this. Then I see distance. I see distance. Then I see mass. Then I see calculate the charge of the second mass. So in this kind of question, charge and mass has business. Are you seeing it? So if that be the case, there are two formulas we can put to use. Was electric field intensity mentioned?
No.
Nothing like that, but distance was mentioned, Shady?
Yes.
Okay. So we will use the same Coulomb's law, but this time around F will be equals to MA. So MA equals to KQ squared over R squared. That's it. Because they're asking us for two things. They said charge and mass. So I can claim. Can I?
Yes.
So please, read that question for me. Let me see if what I have is the same thing you have, so that there will be no mistake.
Well, leave a microphone.
Which one are you using? Medicine. No, don't do it. The one I have here is medicine. Old student, like people using that of
Electromagnetic.
So
That's why I'm using.
no, I'm using this one.
This one.
Yeah.
This one is electricity and electromagnetism.
That
one is
Yeah, this is the one we are using.
Okay, see people that are using this one. That means this one is the correct one now. This is the correct one. Yeah, this one is the old one. I thought medicine students, this is the one they are using. Okay, this is the one medicine. This is the correct one now. I don't know what is happening to me. Read from that one. Read from that old one. That's the normal, the one I know, sir. This one is new to me. Somebody gave me that one, I snapped it.
It's still the same thing.
Is it the same thing?
Yes.
Marie, let's hear you.
What chapter is what?
Number
Page is that?
8.
For you, it should be number 7. For them, it's number 8. 7B for you. Where they said, when two equal charge carriers separated. Okay, let me read it. You check it if I'm correct.
When two equal charge carriers separated a distance of 3.2 times
2.3.
Is it 2.3 or 3.2?
2.3.
Isn't it the same
Wait,
thing?
what did you say?
Okay, this one is 3 points.
This one is 3.2.
Okay, 3.2. Well, you see, that means it's almost like it's different now. So what we use 2.3. What the hell is 2.3? But you see that.
the same thing with our own. Like, you are using the same thing.
Yeah, that's 0.2. It's same with
Okay, 2.3. In a vacuum, I like to move under the interactive electrostatic forces. Then they give me M1
6.3.
times.
There is
Or minus 2 kilos.
Yes, say minus 7.
Okay, that was the same minus 7.
Yeah.
Yes, minus 2.
Minus 2.
Wow. Then,
So I'm trying to change it also.
then acceleration
Yes.
of the first mass, 8 meter per
9 meters per second.
This one.
First
Yes.
Okay, yeah, 8 meters per second squared.
Then the M2, they did not give us.
Yes.
But they told us that the acceleration.
It's 9 meters per second.
Calculate the charge amount of second carrier.
Okay, the next is calculate the charge
Mass and second carrier.
and charge of the second carrier. They said calculate the
The charge and mass of the second carrier.
Wait, they said calculate the mass.
The charge.
The charge and mass of the
Calculate the charge and mass of the second carrier.
Okay, hope you know. Watch something. If this is Q1 for the first charge and Q2, hope you know. Okay, I have this. Did they give me any charge at all?
No.
We are using 1.6.
Oh,
They did not give me any charge, Shirley?
No. So
I don't know this charge. I don't know this. Don't worry, we'll get there. So let's solve. Can I get it?
yes.
If you make A in first semester physics, this semester you should make A plus. Because this one is simpler than first semester.
According to the calculation.
You see this one?
This minus 3
All these things, you will get used to it. As you solve, you get used to it. Because it's just what calculator can do for you too. Do you know what you did in first semester? Do you know simple harmonic motion that some people hardly survive?
And simple pendulum.
So there are plenty things you did in first semester. This one is just focused one place. You do optics, refraction. They tell you concave when it is going inside. Converse. Very straightforward. Okay. Now let's look at this. I know that F is equal to KQ1 Q2 over R squared. But notice that in as much as I have charges moving, I will normally say that the forces of the charges is given this way. But notice that in this case, it's more like where they are telling me the first force is having M1 A1 is equal to KQ1 Q2 over R squared. Then it's more like they are telling me again that this force also has M2 A2 is equal to KQ1 Q2 over R squared. Very important to note. Yes. We'll see what we'll do. So, but why I'm putting it out this way so that you don't go and mix it up. You don't come and do A1, A2 and put it together. So have it in mind that what they are trying to tell you is when you are finding this force, and there is a force, these charges are moving. But the force here, they have when the mass and acceleration on this particular force is directing this body, and this is what we have for it. And there is the second mass and the second acceleration directing this charge and this. So due to the electrostatic forces, if you read that question well. So if I now want to get Q, let's say I want to get Q here. Let's say I want to get Q here. What I will simply do is to say that this thing is the same as saying M1A1 equals to KQ squared all over R squared. Are you seeing it? Yes, sir. Yes. Don't ever make the mistake of solving maybe taking Q1 to be 1.63 something, and then you are taking that Q2, you are going to solve for Q2. It's either they give you different charges, or if they did not give you charge, you equal everything to be the same thing. So for the fact that they did not give me charge, they are telling me to find it, it's simply Q I'm using. So I'll make Q solid of formula here. So that by the time I do it, and I say that this is going to be the same thing, I say, let me make solid of formula from here. And it's going to be solid over 1, cross multiply, so that I have Q squared times 1, then equals to M1A1 R squared. So making Q squared solid of the formula all over Q. This will cancel this. So that I now have Q is equals to square root of M1 A1 all multiplied by R squared all over K. So this is the formula to use and find our Q. This is what you must use. Please note it somewhere in your notebook. If I'm giving different charges, best. But if I'm ever to find charge, I cannot find one charge and then say I'm finding the other one. No, I should equate everything to Q squared. So note it however you can use and remember it. So that if I do that, I will now substitute. So I'm coming. That means that here that I have this thing is equals to this. Hello, watch. M2A2 is equals to this. And notice that M1A1 is equals to this. Is it not the same thing they are equal to? So according to Newton's second law, we can now say that M1A1 is equals to M2A2. Do you still remember it? Newton's law. Where we normally say that action and reaction are, sorry, Newton's third law. What am I saying? Yes. Newton's third law, that is forward and backward forces are equal. Do you remember? So if I have two forces here, let's say M1A1 and I have this one, these two forces are equal because of the fact that this, first of all, let's say this is the backward load, this will be M2A2 minus M1A1 is equals to 0. This remember, first semester dynamics. So that by the time it crosses over, they are not equal. The minus sign will leave. What they say, remember, forward minus, normally do forward force minus backward force equals to 0. So if it crosses over is this. So from that Newton's formula, that's where we get this.
The second question, this is the formula.
No, we are still in the question, but to find that place where they are asking us to find second mass. That's yes. So from Newton's third law, that's what I'm doing, where I'm getting it from. So we can say from Newton's third law, which we did in dynamics, from Newton's third law, which says forward and backward are equal. So if I know that action and reaction are equal and opposite, so if I know that, we are getting this. So that if we want to get M2 now, we can now do M1A1. Maybe it's M2 we want to get. So now M2A2. So we divide by A2. So this will be by A2. This will cancel this. So M2 will be gotten using this. So don't forget it. And somebody might want to ask me, how did I know? How I know is because they gave me mass of the second one and mass of the first one. They gave me acceleration of the first one and acceleration of the second one. So they're giving me two forces. So those two forces are equal. So if I know this, let's now try to solve. Let's now try to solve. Okay, I can now, have you copied this one? Can now, so please, when you are treating charge, there's a reason why I'm telling you to have those two formulas in mind. Have this course in mind like this. If you hear that force inside the electric field is QE, that Q is charge, this is electric field intensity. This one is more like what acceleration is doing, what mass is doing. Also know that this can be sent as MA equals to QE. Then when you come to Coulomb's law, we know that F equals to Q1, Q2 over I squared. This can also be sent as MA equals to this or mg. So this concept idea guides majority of the calculations in unity. Let me clean this part. So I now have Q is equal to square roots of M1 is 6.3 times 10 raised to the power minus 2, then times A1 is 8. R squared. This has about 2.3. 2.3 times 10. If you check, even that's your chapter 2 proper, you will still see where you are doing things like vector. Those things we did in vector differentiation.
It's 3.2.
No, we're using 2.3.
We're using 2.3 from the other textbook. But you can use this concept now and solve using 3.2 to see what you will get. So now you do K. Remember that K has a value. 9 times 10 raised to the power 9. 2 meters squared per square coulomb. So remember, it's I have 9 times 10 raised to the power 9. Okay. So I have punch. Let's see what you have. So please tell your friends, anybody that can calculate that ES plus, we're selling it 7,000. The other one, the second brother to it is 5,000.
This one.
Yes, ES plus. They will write it on top of it.
How much?
Is it FX ES
This
plus?
one.
Let me see. Let me see.
90.
This is ES plus. 7,000. ES plus. Is that one that is the highest? That one is like that one. Higher than ES plus. Are you sure? What's the name? What's the name?
I think this guy has it.
In Casio, ES plus is
Yeah,
what? ES plus is regarded as the highest. It's not a calculator. No, there are things that this one.
I'm not talking of this one.
This one can solve the mathematics you're doing this semester. There are things, tricks.
This one,
Can carry this one.
This one have conversions.
Yes. Yes, that's why there are some things.
Graph.
No insults. Okay. Alright, let's continue. So I can, punch, let's see what you have. What do you have?
17.2.
For everything. Alright, check if it's correct. Wow. Now your calculator. You will check the mode. Okay. Check well. Punch everything here. You got
17.211.
Is it cash?
21. 17.21.
Everything.
Times 10.
You people should check it now. That's my final answer.
ES plus I have punch.
1.72 times 10 raised to the power minus 8.
1.72 times 10
Raised to the power minus 8.
Wait,
Okay, Q is equals 1.72 times 10 raised to the power minus 8. Okay, check. I think what happened to you is something. You did something wrong.
This one is 6.3 times 10 raised to minus 2.
Yes.
Minus 7 here.
Yeah, there was 7.
I thought it's different value.
It's different. See, use this our value. Use this our value, so that when you now go home, those of you that have different value from what we're using in class, you now use that your value and practice at home. So, but for now, let's use this our value. So, check if we are correct.
Yes, you are correct.
I think they changed this board. It's not the board we used last semester.
It is.
Is it the same?
Yeah.
It's looking white and shiny now.
It's not the same.
They changed it.
Should we change the board? Last semester board is not this fresh. Yes. Last semester when I was enjoying myself. So. You got 1.72.
Who got this answer?
Wait, are you ready for your answer now? But you listen now. 6.3 times 10
Let's work it normally.
Okay, I did it this way. 6.3 times 10 is for minus 2. But you can employ this is just 6.3 times 8.
That is 0.504. 0.5.
That is 6.3 times 8.
Yes.
0.4
times the 10 is power minus 2.
50.4.
Like 6.3 times 10 is power minus 2 times 8.
Okay, you got
0.50504.
like this.
Yes.
Okay, times 2.3 times 10. You remember that this one is square. You take the square of this one. Hope you remember. Do 2.3 times 10 raised to the power minus 3. 2 times. 2.3 times 10 raised to the power minus 3 times 2.3 times 10 raised to the power minus 3.
5.9 that is power
Minus 6.
minus 6.
So at this junction, you can do these 2 times this, then divided by 9. Then using this is for the 10. So just do what you do for me, let's check if it's the same. Just do for me 0.504 times 5.29.
So it's not the same thing.
Okay, it's not the same with this one.
No, it's not 2.97. But the other one.
Remember the square root
Well,
sign.
there's no difference.
2.3.
2.96.
Okay.
2.9624 times 10 is power minus 16.
If everything.
For everything.
It's everything with the SCM, with the square root.
No.
Okay, you've got everything
So
divided.
that is minus 6.
Okay, minus 6. Take
Minus
the
16.
Okay, take the square root.
1.721 times 10 is power minus 6.
Times 10 is power minus. That means you are correct. Okay. It's here.
But the answer here is 1.796 times 10 is power minus 10.
Minus
10.
10. Okay. The book gave you
796 times 10 is power minus 10.
minus 10.
The value you use is 3.2, not 2.3. It's 3.2.
Okay, that means the book actually is 3.2. That's why it got that. Please, what we are using for our own is 2.3. You see? So this is what we are having. And then you've learned things. You will then go and write. Yes, and use your own. That value 3.2 to see if you can get what is in the textbook.
This is not
It's not.
Are you sure? You're using 3.2.
Yeah, 2.3.
No, now what I'm saying here, they are saying that 3.2 is what was used. So what you do is,
This one is 2.3.
yes, now the answer they gave
Okay,
is the answer of 3.2.
Okay.
Wow. Please, can you do something? Do you know what you're doing? I've told you, those of you that have those textbook, go and look for somebody that has the other one. Join the two together. You sit and read it. You read this one, you read this one. This one, Be using the 2. So that you avoid the mistakes. Don't worry, Daniela will help you with genetics. She's starting class next week. So try. You've not done genetics now? It's parascology. Okay, genetics is very easy. Alright, let's find M2. Let's find M2. So to find M2, simple. I'll just do M1 is 6.3. So you can even do this one, but let's do it for the sake of people that are watching our class from house. So we do 6.3 times 10 raised to the power minus 2. Then A1 is 8 all over 8 all over. A2 is 9. So punch it, let's see what you have. So punch, let's see what you have. Because I noticed that
0.06.
0. Okay, M2 is equal to what?
0.061.
0.061. Like this?
No, 0.0.
Okay, so, sorry, wait. Jesus. 0.061. Thank you. Like this? Okay. KG. Finish. Please check if it's the same thing you are getting. Check if you are having the same thing. Punch your own. I'd not say check your textbook. Because I will show you what textbook did. That is not wrong, but it's not right. Because that your textbook, see what you have here. I saw where Rita was solving this. She came to show me. They did M1, A2, all over A1. That's what they used to solve the other day, which is not correct. I said that is you punch, you do not get 0.061. What? 0.056. That is approximately 0.06. It's the same thing. Let's leave it at that. But see what I want you to do now. Check your textbook now. Is it the same answer they have?
5.6 times 10 to the power.
I see. See, do this thing. Do 6.3 times 10 raised to the power minus 2 times 9 all over 8. This is not right. Do it. Let's see if you have that in the picture. I check your option here. The two books.
For my own is 5.6.
I'm having 5.73 times. Square root of 5.73 times 10 is the power minus 21. For cube.
No, I'm telling you to check the answers.
M2, no, M2 is 5.6 is correct. For me, it's correct.
Okay, they gave you 5.6 here.
5.7 is correct. For M2, it is the cube that.
Mass of the second kind, yes. Okay. Can I claim? Can I claim? Yes, I can claim. You said this one did not give you, this one gave you 0.7, Shebi?
0.7.
That's what I saw in the book. I'm surprised that I'm seeing 5, 6 there. Well, see, let's check something. If I have M2 equals to KQ squared all over R squared A. 2. Hope you know what I'm doing here. See, I'm doing m squared a squared equals to k squared r squared. And we know that the q we've gotten is the same thing for all of them now. Shebi, we got q to the what? Give me the value we got for q. 0.7 or 1.717.
1.7211 times 10 raised to minus 8.
1 times 10 raised to minus 8. Okay. M2 equals to 9 times 10 raised to 9. And Q 1.7211 times 10 raised to minus 8 squared. See how I do this at home. Which one? So which one is wrong?
That one they say M1A2.
You already push the answer yourself.
Let me on Which one?
M1 for you.
That is the second one. Okay. But you got this one for M2, Shelly. 0.061. You know why I said you should?
That's 0.056.
You got 0.056. No, why I said this one is that when Rita brought it to me, this is the one she showed me. I was thinking when we did this, something like this, we got an answer in her textbook that was different from the one we got using this our own. You got 0.061, approximately 0.06 for this one. Is it not? When you
maybe 0.060.
0.060.
Yeah, but we're not going to be 1.
Okay, but I want us to test something. I'm coming. So let me abandon this loop that I have here. Let's just do something. So I have r squared.
2.3 times 10 raised to minus 3.
Square. Then I have my a2. My friend said, when you go see it twice. Wow. Punch, let's see what you have. I just want to check something. I want to confirm something. When I said we try this, is I solved this, but you know that sometimes you'll be in odds, the people will be breaking works for you. So Rita brought something like that, and we solved it using that one. We saw something inside that textbook that makes sense. Just thinking. Punch, let me see what you have. Eh? This is how to go about it. So this should be your final. This is how to solve this. Eh? But I want to check something so that I will see if that is what they use to get that value exactly that is in your textbook. And we did not approximate anything here now.
And you got 0.056.
Here, you got 0.0. You watch everything here. And empty gave you what?
0.056.
6, Jimmy? Engaging. That means, hello? Yes. You know, I normally tell you.
So they approximated this one.
See, hello? As a student, pay attention. You see that need to pass. Shall we know?
Yes.
So that is why I don't teach you one and say let's insist on it. That means by rights, this will work. Assuming we are not talking about charge. Hello? Assuming we are not talking about charge, this will work using Newton's third law. But since we are talking about charge, this answer is correct. This should be the correct one. This one gives you approximately the same thing, Shelly. It's to show you that Newton's law works. But please, as my students, stick to this one.
So please explain this.
This one?
But on the textbook, it's 5.6 times 3 raised to minus 7.
Yes, that is
Okay, they put minus 7.
Yes.
I wonder, you got exactly minus 7. You got exactly minus 7.
M1 M1, A1 is equal to M2. That's what I use.
Okay, and you got to raise to power minus 7.
Yes.
Are you sure?
Yes.
Who can
M1, A1 is equal to M2.
Okay.
Are you sure?
M1, yes.
Yeah, that's what I use.
Change the state.
Hey! Blood of Jesus.
As neighbor, like
Blood of
What we are trying to say is that instead of use M2, use M1.
Okay, instead of M2. Like instead of doing M2.
That is, I've gotten the M2.
Eh,
Just leave the M2 and something for the child, use the M1.
Then M2 times.
okay. That is here now. So.
Yes.
Yes.
Okay.
no understand.
That means if I have like M1 equals to KQ squared, see what you mean? All over R squared.
Yes.
That's what you mean. Okay. That means I should
Give
have.
the acceleration.
Okay. That means the acceleration of this is the one of A1 now.
Yes, that's yes.
So that I now have.
I don't understand what
It's
that
one of
I'm
the
coming.
two.
Don't worry, I'm coming.
Yes,
I'm coming. Okay, is it what he got? Using M1, A1. He gave you raised to power minus 7.
Yes.
That means calculate all with the problem now.
Sir, all you see on board, it's a bit.
Yeah, put that to you. Wait to see.
One.
M1, A2, Sherry.
Yes.
It was M, sorry, A1 now.
Yes.
M2, A2. Yes. Sherry. This should be equals to KQ square over R square now. So when I'm doing this one, I'm having this in mind.
But let's use this first one, M1.
Sir, problem is now this was single minus 7, not 2.
Okay. Yes, I think that's true. But is there anybody that is only showing 6.3 times X minus 7 here? Is
Yes, his own is minus 7.
It's minus 7.
Okay, you minus 7.
Yes.
So that's yeah.
That means that if I use this one, I use this one. I'm still correct. Well, please, this little stop law, if you try it, I prefer you using this one because there is charge on it.
Okay.
Well, please, remember everything I'm teaching you. That's why you are learning.
Just an answer that giving us 6 minus 7.
So what you will do if you really want to help yourself is to make sure you snap all the questions. This one's one and this one's one. So that you use it and go home and solve. So we are correct with what we are using. That's what it is. What we are using, we are correct. That's kind of what we are using. Ask, my friend, ask.
Okay, now I wanted to ask you, like this one has 10 minus 7 and you use the same.
Yeah, this one has minus 2.
That's what I'm saying.
The
They took the answer of
The answer, yeah,
for us, but with different values.
You see my own? Okay, see the charge.
The chart here, the got. It's not correct.
No, don't doubt the textbook. Don't doubt anything.
They know what they did.
Yes, anything we are doing. See, what you will just be doing is to be checking our own value, how we are using it.
Yeah.
Because most of the time you see that it's our approach might be wrong.
Minus 2, they use minus 7, and they solve exactly the same.
Before you check the answer, use the two ways, use the two questions. One will give you exactly
I
the
think
same
they're
answer.
taking their own
I'm
answer.
using it's the same formula.
See what
Different
I
values.
see what I mean, The value you use, use a value that is inside that medicine textbook. Then use a value that is inside the other textbook. Compare the two, you get an answer that value with that answer. If you use the two values.
I thought you got the answer.
Your own value.
So please,
So like they're trying to confuse us or what?
we are correct with what we
Yeah, we
are
are
doing.
correct.
Yes. So please, what you will do is when you go, you will not try this work using that 10 raised to minus 7. But with what we have, we are correct. So please, let's try to see that we solve all these questions. So let's move to the next one.
What is explanation will be problem for
So
us.
Okay. So, is it the raised to power something?
I like solving it on my, like, before I don't press, I solve.
Okay, that means if, for example, how you can be doing it is to say, for example, how I have this, I can say 9 times 1.721. Are you seeing it? Then I push the tens one side.
Yes.
Times
Raise to power.
times 10. 9 9. So you see that this is
-8.
-8. I noticed that, sorry, before doing it, if you do it 1-1, before the problem might be you might end up forgetting it. So square this value. When you square it, what do you have?
Okay.
That is.
I want us to solve this one on my book. Let's see if maybe if I'm the one getting it wrong.
You are giving him.
Okay. The chart, let me just give you the mass is 6.3 times 10 to the power minus 7.
6.3 times
10 to the power minus 7. Times 8, which is acceleration. Yes, ma'am. Times 8.
Okay.
Then times 3.2 times 10 to the power minus 3. Yes, square.
Okay, 3 points times 10 is power minus what?
3 square. It's supposed to be square now.
Like this?
Yes.
Like this? Check
Yes,
it.
then divide by 9.0 times 10 to the power of 9
The distance.
to the power of 9.
Like this?
Yes. You know, with this, we are calculating for charge now. Then everything is square root of everything.
You know why we are having different answers? We are not using one value.
No, I want to see what I'm doing is that I want us to do this one so that let's see if it's the same.
Okay, but you gave me 3.2 times 10 to the power minus 3, should you?
Yes, minus 3.
Okay, one do for me. 3.2 times 10 to the power minus 3 times 3.2 times 10 to the power minus 3. Just do it, let me see what you have. Give me the answer.
3.2 square is 10.
No, what I want you to do for me,
10.24 times 10 to the power of minus 6. That is what it's supposed to be.
Okay, then 3.2 is what?
10.24.
10.24, like this, should be?
Yes.
Okay, times 8 times. So please just try and pay attention. What I want you to note here is, in any case where you find it hard to use calculator, you can just use this method. So what I will simply do here is to collect.
I can do 1 point. I can change that into 1.024 times 10 to the power of minus 5.
Yes.
Yes, you can do that. You can do that, but wait, but see, when you punch this thing on your calculator,
Yeah, that's an insult to minus.
It will still give you minus 6.
it's minus, there's minus.
It is
But
minus.
I think it's square, so it's minus
It won't
1 to
disappear.
9.
No.
Oh, yeah.
Power.
It should still remain.
Okay, let's just go ahead and do 6.3 times 8 times 10.24, then times 10 to the power minus 7, then plus minus 6, which is minus 6. So remember, this is add the powers.
Yes.
So I'm just adding up the powers, and since it's minus, it's
Then you can take the 9 off and you also minus.
Don't worry, I'm taking it one at a time. Remember, the goal is to not confuse and make mistake. Oh yeah, just punch for me 6.3 times 8 times 10.24. Let's go.
That is 560.096. 516.096
Okay.
times 10 raised to the power minus 13.
Okay. Yes. At this junction, I can also. Should we copy this one? Yes.
Minus 7.
Oh, you got 7. Oh,
Yes.
sorry.
Yes. So I can now do 516.096 over 9 times.
Minus 9.
Hope you know why this 9 is minus. So I have bought from me 516.096.
Divided
7.34.
times 10 to
You say if I can.
Yes.
Yes. Is it what you have?
Yes.
This is what we're getting.
Yes.
How? Objection. So minus 13 minus 9. Is
It's
it
minus 22 now.
Minus 13 minus 9 is not 22. Minus 22.
Minus 13.
This 9 can stay for 9. So minus 13 minus
Minus 22.
minus 22. How now?
No, see how you do it. See how you do it. See 13, there's 10 inside, shall we? Carry the 9 and put inside 10 is 19. Remove the 3. So if you carry 3 and put to 19, it will be 20, 21, 22.
It's 22 now.
What we had before was
What I'm saying here.
don't worry, time is going for that one. Before we finish. Use calculator now. You just see, I think. Okay, we'll still take the square root, shall we?
You see square boy, let's do it. I've done it and it's not tallying with what you have.
I do. But watch the square root lesson. Yes, sir. Minus 6. 11. Okay. 7.573. Okay. I think why this thing is happening to you, I think it's from the value you use, which is this 3.2. Remember that our own is not,
Which means the mistake came from them, not me.
we will use 2.3.
Yes,
So this is what we use.
3.2. Which means I'm correct now.
Not you. We are correct.
Is it correct? Is it correct?
What do you mean I'm not correct?
Lord of Jesus.
You're correct. Sir, this is what I got. And it's not the same here.
Try using our own value.
2.3. With the same, you see, should I use the 6.3 times 10 to the minus 7 as a mass?
No, use raised power minus 2.
Okay.
That's what we used. Shall we?
Yes.
We used 2.3 and minus raised power minus 2. So I just think the thing fluctuates.
From them, from
Yes,
the type.
yes, fluctuates. So but I know that if you try different ways, the key thing is knowing how to solve it without making mistake. Knowing how to solve it without making mistake. So do you know that what it means is that even if you fail to remember that Newton's third law gives you force equals to force, if you go back and use the idea that since you've gotten charge, put charge and substitute and you will still get the same answer. That's what it means. So let's move to the next question so that we can be fast. You see that we need to do that chemistry.
Yes.
So let's not delay much. So there's a question there that says what you are using is that the value, the one we solved on the board, is correct. So if you are using any different value, maybe in this textbook or in this textbook, you try and solve using that value. So that's what it is. Check. There's a question that says, please let's solve this I9CII so that we can now quickly move to number 10. All those other 9CII. Yes, 9CII. All those ones that look like GST questions, I've solved those ones. You will see the video. The GST parts, you just watch it, learn it as you are reading. So what we're doing is calculation. So let's solve 9II so that we can quickly solve number 10. We'll call it a day for physics today. So that we can do chemistry. So in our next class should be on Monday. So we'll try and fit on Monday. So in our next class on Monday, we'll first do maths. So after the maths, we'll now go back to our physics. We'll now do chapter 2, calculations. Then do introduction to chapter 3. That's how we do it.
Is it only Saturday and Monday there's tutorials?
No, we do tutorials every day. Why we shifted to Saturday and Monday is because of the practicals. We did tutorials on Tuesday now. Wednesday we were supposed to do tutorials. I learned people are doing practicals. The same thing Thursday. So for everybody to be among, that's why we shifted it to this. But Tuesday we still do our tutorials if there's no practical.
No.
Even chemistry practical.
Okay, on Tuesday. Wow.
Everything is week now.
But before 4, we then have to do. The practical should be done before 4. Wow. Don't worry, let's for now think about our class. Before that time, we'll definitely find a way to
When we reach the feedback,
If you notice, once we are serious with class, we always have class. So I believe we'll find a way to make sure we do our part. So please, and if you notice, all these parts you see me written, these are the parts I know that they don't play with. So I make sure that I first read all those chapters they don't play with. There is a reason why I started chemistry from chapter 2. Please. So when you go home, still try and revise chapter 2 that we did the last time. We'll revise it together too. So that in our next chemistry class we can start you see chapter 3 for equilibrium constant, equilibrium. So please look at this. They said calculate the charge required to raise the potential of an isolated metallic sphere. Question 9II, 9CII. Calculate the charge required to raise the charge. Required to raise the potential of an isolated. Have you seen it? So that I will not be reading. Calculate the charge required to raise the potential of an isolated metallic sphere of radius 2m from 0 to 3.4 times 10 raised to the power 5 voltage. Full stop. Calculate the charge required to raise another metallic sphere of radius 0.8 meter to the same potential. Okay, so that is question 9II. It might be different in some person's own, some department's own, but if you have it, it's very simple. Let's just see how we solve it. The first method I normally tell my students in solving question is right? Yes. In fact, sometimes if you write this in solution, this thing has saved a lot of people. Yes, and sometimes when your handwriting change, you take it slow, inspiration will be coming. Yes. So you now come and write out everything. So they said charge Q. I don't know it. Don't mistake charge with capacitance. Some people will rush and start reading chapter 3. And when they come back to chapter 2 and chapter 1, their head will be doing the which one is which one. That's why I normally tell you, take it one chapter before the other. Potential V. To raise the potential V of an 0 to 3.4, I have no business with 0. Just 3.4 times 10 raised to the power 5. That's what they're talking about. Then the next thing, calculate also the charge required to raise another. That means this question is like 2 questions in one.
Yes. So what do we do?
Yes, then.
Please, what question?
Number 9.
9II.
C.
9CII, yes, 9CII.
It's not here. It's not here.
It will be there.
Calculate the charge required. Calculate the charge required. You've not seen it?
It's not there. We don't have it.
Okay. Wow.
But this man can be devilish and
You have seen the limitations now.
I said,
You come to my class.
you would fail.
Yeah, you are. Don't need to
Okay. I see. Do you remember? Please, do you remember? Watch. Always remember that voltage is very simple. Potential. We say that it is what? Work done.
Overcharge.
Very simple. The work done in moving a unit charge from one point to the other. You did with it. You come and replace. This is how I like solving my own. So that you don't run anything. Fs over Q. We don't have business with S. We put it out when we're talking about electricity. It's radius, not S. So just like when something is climbing up, you don't have business with S but H. What do you know? So that is physics for you. So if I know this, I know that this thing looks like E, should it?
Yes.
But if you notice something, what they are asking me here is for charge.
So no need of removing it.
Yes, no need for removing it, but notice something, they did not give me force. Should we see it?
Yes.
This is why it is important for you to know all the formulas you can derive from this. So you need to remember that F is equal to K, and K is a constant. Anytime you are solving anything electricity, K is a constant. So the only time you don't put K to be this is when that electric constant was mentioned. If they mention that electric constant, you now use K to be 1 over 4 pi E. And if the electric constant is given, instead of you suffering to find anything, the day you get electric constant is like 3. Just go and do, instead of you do 3 EO. Very simple. So if I know this, I know that this is Q squared over R squared. So I can replace this.
What if you solve a different thing?
Okay. But okay, that means that V is equals to K for F.
let's solve for F.
KQ square over R square. This is F, it should be known.
Times by
Then times R.
cube.
I'm coming. See now. Everything F
But
is
it's cube there.
I'm coming.
R.
Everything. So let me say I put this R here.
Q is supposed to join.
I'm coming. I have it in mind. Divided by Q. Divided by this Q. Why I'm leaving that Q so that you don't come and put it here. Once you put it here, it becomes plenty. So that I can now introduce reciprocal law. And reciprocal law says, do you know that this can cancel this?
Yes.
So that I have over R. So that reciprocal law says that if I have division, if I introduce multiplication,
Yes.
now it's 1 over
Q.
This can take care of this.
Yes.
So that V is equals to KQ
Over
over
R.
R. So it's important to note this. You also need to note, you can prove somewhere to you that electric field intensity is equals to KQ square over R square. Hope you know.
Yes.
We can prove that too. We can prove that. Because you remember that V, do you remember that V is equals to ER?
Yes. Yes.
V is equals to ER. So let's say I make E solid of the formula now. So you see that this will be E equals to V over R. Shall we? And V is equals to what? KQ over R. Is it not possible? So divided by R over 1. So that's KQ over R times 1 over R. Shall we?
Yes.
So that you now get KQ over R square. Very important to note. These are different relationships, different ways to connect it. So if I know that means that I can just replace this, I don't have to suffer myself. I can just say, okay, this is KQ over R. Now carry the parameters and put so that I have 3.4.
Times 10 raised to the power.
And you cannot forget this thing once you remember this formula. Once you always remember this thing, you can never forget it. That is work done over charge. So anytime you just remember Coulomb's law in place, do it. Alright, times Q. I don't know it. Okay, equals to 9 times 10. Then I don't know Q, really?
Yes.
Then I will come 2 meter. All of
That's
So if I cross multiply, can I claim?
Yes.
If I cross multiply, this will now be this will now be the sentence as saying 2 into 3.4 times 10 raised to the power 5 is equals to
6.8 times 10 raised to the power 5 is equals to 9 times 10 raised to the power 5.
Okay, for which one? Is it for this one?
Yes, that one.
No, say that this man write this book, so you might not say something.
This is the one. You will be so many students. If you reach Parkland, you will worry them. Alright, so you got 6.8 times 10 raised to the power
5 raised to the power 5.
Okay, 5.
Over 9 points.
Okay, 9 points. 9 times 10.
Raised to the power 9.
I have punched, let's go.
7.5 times 10 raised to the power
7.6.
So Q is equal to 7.6
6 times 10 raised to the power minus 6.
minus 6. Okay, and you know it's in columns. I see what you do for me. Classwork now. There is a second part to that question that says, calculate also the charge required. Have you seen it? This is not my WhatsApp phone, so I can't share it on the group now, but somebody with it, just check and then send to students. Calculate also the charge required to raise another metallic sphere of radius 0.8 meter to the same potential. Calculate also the charge required to raise another metallic sphere of radius 0.8 meter to the same potential. So please, if you are very observant, the reason I started with ground law today is because that's the most parts that will disturb you. Don't worry, we will still do it. He simply talks about the relationship between electric field flux. Yes. So he's simply trying to prove electric field, the relationship between electric field flux and its ratio to permittivity to electric field intensity. We've already done it. Okay, we gave it as Q over E naught is equals to E A.
Okay, A is area.
Yes, and this is electric field intensity. This one is charge. This is permittivity of physics. You will see the video this night.
My YouTube is blocked. So
Okay, but you can be using Chrome now.
Chrome.
Or inside the app. Because you paid us for tutorial lessons.
Yes.
Do you have the app?
I do.
Inside the app, you will see it there.
Oh.
Yes, it will be there. Or maybe before you leave today, you remind me, I'll send you the video via Zenda.
Okay.
So that you can go through it. Because if you copy it like this, if you go to textbook, you might still get confused. There are certain things I said there. So solve that classwork so that we can now do number 10 and then we are sure that we are done with everything exercise for chapter 1. No, it's chapter 1. We've not touched any exercise for chapter 2. I said in our next physics class.
No, it's still chapter 1. There's this question here.
Calculation?
Yes.
Okay.
It's a product of electric dipole moment. Where they give E is equals to P over 4 pi epsilon 0.
Let me see.
Number what,
The product of dipole moment.
Dipole moment is under chapter 2 now. Yes. Dipole moment, even where you are doing constants, is because why is it so? Because in this your O, they are combined chapter 1 and chapter 2. Why in their O, they have only chapter 1 separate. Chapter 2 separate. Anything dipole, are you not seeing it? But chapter 2 is capacitors. But the O chapter 3 is capacitors. Shall you see what I said when we started? I told you that chapter 2 that you have, normally everything is supposed to be chapter 1. They are together. So you have chapter 2 class, which is our next superior class. So, can I claim? So please, your assignment is to go home and do that part, the second part of that number 9 I goes through. The second part of it, where they said calculate also the charge required to raise 0.8 meter distance to the potential. Should it? Yes. So that one is your assignment. 9 the second part. Because that is like 2 questions. Alright, go to number 10. Let's solve everything on that number 10 so that we can call it a day for physics.
We have more students in this work.
Okay, when are you submitting the workbook?
Wednesday, 1 to 19.
This Wednesday.
Wait, I think they said we should talk about this.
90. No, 90.
Yeah, 80 to 90.
Yeah.
Is it that day you know on Wednesday or Tuesday?
I'll post some videos. I'll post some videos on it on Sunday. I'll post the link on Sunday. So 1 to 90.
Like, what we were doing.
90. Okay, please.
What's it?
Okay, the question is 1 to 1 day.
Yes, correct. Richard, you're not doing something.
Wait, the question is 1 to 1, I think you want to 90. So what is the
The remaining for quiz.
Okay, that is already 10.
Yes, for quiz.
Don't worry. Don't worry, it's almost over. In next 4 months. The next 4 months, we are 200 students.
which 4 months?
Shall we start to 4 months?
Bye to physics.
Oh, you'll be doing chemistry, you'll be doing things like chemistry and biology.
No.
You be doing physics, yes, I teach physical sciences. Yes, even ODE, yes, even ODE. There's some of you who now go and do organic chemistry. Some people will move to Parkland.
Anatomy and physiology.
And are there.
Our
But those of you in France, we will still be meeting in 200 level because we're doing
You will go to 300 level, sir.
today organic chemistry.
That's if you are in industrial chemistry.
We-
Can be sorry.
Can you see for life?
Yes.
There is a
Sometimes you will go there, sometimes you stay here and see your class. Anyone that requires you, like all those physiology, anatomy courses, I think that's the courses that require you. Like there are some courses that you do. They're called physiology and anatomy. All those thoracic of the limb. Yes, okay, it's true. Let's continue. So when that time comes, I will show you. So number 10. Number 10. They said an isolated conducting sphere. A. So let's say I have a sphere. Let's say this is the sphere. As the residues. So I want to call this stage. So as the residues 13 cm. So sphere A or R. Number 10. An isolated conducting sphere A has a radius 18 cm. So 18 cm is the same thing as saying
0.8.
is this about
18.
Chevy?
Yes.
Then they said carries a charge Q of 4.0 times 10 raised to power minus. Is it minus 7 you have there?
Yes.
You know that if they have this to be microcolumn, you should convert it to column.
Yes.
Always remember. Don't say I was trying to be very fast that day. I didn't even remember. Remember it. So convert to the unit. We even learned all these things first semester that unit is important. So they are not telling us calculate the potential of the sphere. That's the A part. This is the best place to get because it covers a lot. From A to G, it covers so much. We can be able to remember how we do everything.
It's there. But the
Potential of the
potential
sphere. And we remember that potential is simply V is
equal to
Q over R. I don't need to discover it again.
yes.
So, and K is a constant.
The first is a calculate potential.
Yes, potential, if they say potential of voltage is the same thing they're talking about. Or they tell you the work done by the charge, they're talking about the potential. Don't mistake it. Don't go and be doing FS there. They're talking about the potential. So,
Can use it as stats, like can use it as stats. Can use it as stats and drive it.
you see which one?
The Fs over R.
Yeah, you can, sir. You can. You can. But just remember that there will be charge, over charge. So,
what question is this one?
question 10. They said calculate the potential of the sphere. So, V will simply be equals to
9 times 10 raised to power 9 multiplied by 4.0.
yes. I even need to put that point 0. 0 has no use. All over R.
0.18.
So inside the exam hall, you don't need to be suffering yourself deriving. Once you hear potential voltage, Q over R. If it's electric field intensity, put square to the R.
Okay, if electric field intensity.
Yeah, Q over R.
And if it's electric field intensity, just put R square to the R. Very simple. And how do you remember all this? The key thing is to always remember that law, Coulomb's law. Force directly proportional to the total of charges. And inverse of the distance. Times everything here. Give me the answer.
Above minus 5.
What?
2 times 10 is above minus 5.
2 times 10. Like this.
Yes.
2.0 times 10 is to the power minus. Times 10 is to the power 4.
Is it 4 or 5?
4.
Times 10 raised to power
Like 0.00000 times 10 is to the power 4.
4 or minus 4.
Is it minus 4 or raised to
4, just 4.
That means that V is equal to 20,000.
1,000?
Is it not?
Yeah.
That's what it means. Wow. Volts. Fire. Let's go again. Let's check the question for me. Deliver. There's another isolated sphere. Hope you are seeing the question.
Yes.
Another isolated sphere, B. There are two spheres here now. And you've seen what sphere means. You've seen that anytime you have one charge, that the electric field it causes is a sphere. If you have charges, it causes cylinder. Don't forget. And these are Gaussian surfaces. So they said that this one, what's the rate is given for this one?
9.
Okay, 9
centimeters. That is going to be 0.09.
Which is equal to 0.09. Okay. What about?
Same charge.
Okay, that is the charge. Is the same. So Q equals to 4.0 times 10 to the minus 7C.
Then B is equals to KQ over half.
Yes. So that means that V should be equals to, yes, using the same formula.
Then the charge of the radius between.
Exactly. V equals to 9 times 10 this times 4.0 times 10 this minus 7 all over 0.09. Oh yeah, punch. Yeah. What do you have? 40,000. Wow. 40,000. Okay, yes, half of 18 is 9. Yes. Okay.
Then C.
Okay. What C says, if spheres A and B are not connected with a wire, what is the relationship between the potentials of A and B? Okay. If spheres A and B, more like I have A, then I have B should be smaller since it's half of it. So if I have this, let's say this is my B, I'm connected with a wire. Okay, then I ask me what is the relationship between the potentials of A and B? The potentials is that it will simply be the same as saying, remember, this is VA, shall we?
Yes.
This is VB, it will be equal. Yes. It will be equal. See what I mean? Whenever there is a rule in physics that says that whenever charges are connected, whenever different charges or different spheres or different areas are connected, that there will be equilibrium. The charges will distribute until the potentials become the same. So which means that if I have a region of higher voltage and a region of lower voltage connected with wire, the region of lower voltage will distribute to the part of lower voltage until there is balance. So they will be equal. The number, I know what work done means. So the charge flowing from here, work done in moving a charge here. So the work done in moving charge from this point and moving to this point will get to a point where it will no longer be too high at the region of higher charge. They will now be moving equally. You go here, you go here, you go here. So once you are connecting it with wire, VA should be equal to VB. And if you want to represent this well, I believe the expectation is that you need to put KQA over R to be equals to KQB over R. And you know that this is RA and this is RB, shall we? The K is constant, it will always be the same thing. Shall we? And the charges are the same. So I will have QA, RA is 0.18, shall we? RB income 0.09. So let's say I want to make any of these. I believe if you are to represent this is the relationship. This is the relationship. In that part of that question that they are asking you, this is the final answer. The relationship is simply this. But if you really want to solve further, maybe to get what A should be and what B should be, because you know that in mathematics we don't stop at something like this. We don't stop halfway. This thing is halfway. The relationship.
Give you back the charge. Supposed to give you back the charge.
It won't. Listen to what I'm saying. See what I'm saying so that it makes sense to you. See, I said at equilibrium, at point of connecting to wire, there should be equal potential. There should be equal potential. But the only difference now is that the radius of this one and this one is not the same. So let's say I want to make a Q charge on A subject of formula. I want to make charge on B subject of formula. Let's see what it will be in this relationship. But notice that we are now moving away from potential. Because potential, they ask us, this is what we are supposed to represent. There will be equal. But we just want to make sure that we have final for this, final for this. Nobody asked for any of this in that question, but we just have to put it. We can't stop halfway. So I now have QA is equals to 0. This one crossing equality. This will be
0.8 QB over 0.09.
0.09. Nobody asked you to do this thing. That question is just, this is just what you get there. You can even put it. So in the objective part, you see that what they will just put is maybe V equals to VB or V greater than VB, V less than. So this is what you are expected to do. But I'm saying that we cannot leave anything we are solving at this point because this is VB, these are the formulas. So I just want to get what QA is to this, get what QB is to this. So if this go here is 1, go here, what do you have? 0.18 divided by 0.09. 2, Shelly? 2. So QA is equals to 2 QB. Okay. Assuming maybe I did not do it this way, and I did maybe, let's say,
of 1.
Can I claim this?
Yes.
Let's say I did, you said chart of 1.
Like charge, put charge to that QB and multiply it by 2.
Okay, we'll come to that, but okay, put charge and multiply by 2. Okay, yes. Sharp, it will give us what QA is. Yes, but let's check something. If maybe I have QA over 0.18 equals to QB over 0.09. If I make QB solid of formula here, I will have QB equals to 0.09 QA, should be?
Yes, over 1
So QB is equals to QA 1 here, should be 2. QA over 2. So which means that this is the relationship of the charges. That is, what QA is simply 2 times QB. And what QB is simply QA over 2. So how did I get it? From this relationship when I connect with Y. That's what I've gotten, and this is the answer that they're expecting from me. This part, I just solved for them because I shouldn't leave this. So let's check for the D part. Let's check for the D part. So they did not tell me to solve anything on it. I just did this to show you the representation. Okay, they said we charges flow from A to B or from B to A when the spheres are connected with Y. I want us to check something. This is 40,000 volts for VB, Sherry. Why VA was 20,000 volts. So which potential is high? This one, Sherry. That means that electric potential or charge will flow from this one to this one. Wow. Charges flow from region of higher potential to lower potential until they now establish equilibrium. They will not be equal. Please write it down so that you remember it. Charges flow. So the number D part of it. Charges flow. Yes, from region of high voltage. Region of high voltage. Voltage to lower voltage. Do you know how you remember that diffusion? I normally use dilution for it. To dilute something means it is concentrated. You now dilute from high to low. So another way to think of diffusion is dilution.
So what do you say about that charge?
Okay, I said charges flow from region of high voltage to lower voltage. So that means it will start from B and move to A. Until equilibrium is achieved, then there will be equal. So if I know that, let's move to the next part. I'm trying to see that we rush it fast. So in that question, charges will flow from B to A because B has higher voltage. Now, then let's see, you can even see it. You can even see that the charge is going to notice something. QH, and this is 1 QH. How many QB do I have here? 2. They are equal. Are you aware? So 2 of this is equal to 1 of this. So if you have something natural, let's say you have big bucket of water and smaller bucket of water, maybe you connect, maybe you put water inside one basin, then one drum that has big distance, and you come and open maybe a space inside that water. Where will water flow from? The big one now, immediately occupy that small one, it will start flowing away. That's the same concept here. So charge will move from bigger parts, the one that has bigger charge, bigger voltage, the one that has lower voltage. So you need to notice that. So let's be fast. I can't believe that we stayed on physics till 4. So let's. It's 5. We said we are going. So panic less. So calculate also the final charge in each sphere. Calculate also the final charge in each sphere. Okay.
Just add
multiply the 2 to the charge and get A, and divide 2 to the charge and get B.
Okay, and the charge given to us, what charge? They gave us the schedule?
Yes.
Okay, that means the final charge, correct. That means that QB will simply be equals to 4.0 times 10 raised to the power minus 7. All over 2. Hope you know why, because the charges are the same. So QB will be equals to what? 2.0 times 10
minus 7.
And you know that it's going to be in column.
Yes.
Why? QA.
8.0 times 10 raised to the power.
QA will simply be 2 into 4.0 times 10 raised to the power minus 7. So 8.0 times 10 raised to the power minus 7. A-suit is the only place you come and get answer. You come and get answer. You do your one and go home peacefully. You don't know. What we are doing here is peaceful things. Do you know why I'm saying it? There is no question you will see in the exam when they start giving you. The only thing is they will change the values. For majority, who said? That means you did not read for first semester. You see that first semester was more of vectors and all those things. Vision.
If it was better, I'll get it.
No, the missing of what you saw vectors were there.
friction. I can bet on that.
Okay, friction. Which friction? Dynamics. That is dynamics now.
Friction came out more than 10 for me.
Dynamics. That's dynamics now.
My own as a what I'm comparing equation for A and for B. They will not be the same. Like if you use this your equation, which is QA is equals to 2QB. If you QA is 8.0 times 10 to the power minus 7, which is equals to 2 times, which is QB, which is 2 points. Times it will not be equivalent to each other.
They are not balanced.
No, it's not.
Yeah, they're not tending to balance.
Okay, see what I want you to do now. See what I want you to do. You are thinking, but you are thinking with the right tool, the wrong tool. See what I mean? I know that this is, do for me, K into, that is 9 times 10 to the power 9 into 8.0 times 10 to the power minus 7. Divided by RA is what? 0.18, should be?
Yes.
I am doing it for me. Then after it, you do for me 9 times 10 raised to the power 9. Then times 2.0 times 10 raised to the power minus 7 divided by RB is 0.09, should be? What did you get for? Which one?
First one.
40,000.
You got
4.0 times 10 to the power 4.
this one. You got 1 point.
4.0 times 10 to the power 4.
Okay, I think funny this one. So if you notice, what did we get when we did, this is QB. This is QB. QB, what did we get when we did the voltage? Was 40,000, should we?
Yes.
But now this one is giving me voltage of what? 20,000. And this one is giving me what? Voltage of what? 40,000. So if you notice, you see that because of the fact that the final charges rotated in this ratio, their voltages is changed, which means that this one now, this 20 is now equal to the voltage that we got for B before wire was connected. And this one now is equal to the voltage we got for A before wire was connected. I don't know if it's making sense to you. It's making sense. I'm thinking of how I should put it so that you understand. For someone that wants to understand it, will understand it. So before and after, you see that before wire connection, this was
20 and 40.
20. After it, the voltage of this one is now equal to this. When wire was, then the voltage of this is now, which means that they've met at equilibrium, which is what we are looking for. So at equilibrium now, QA is now equals to QB, and QB is now equals to QA. That is what we are trying to do there. But let's check if there's another way to explain it. Because
that's in 0.18.
Which one?
Is that in 2?
0.5.
I did like if you divide this 0.09 here, 1, go here, 2. Is 0.09 going to 0.18 to 2? So let's see if there's another way I can explain this to you. I have Okay, see here. Notice we use their final charges, right? We use their final charges to check this. And you know that these final charges is when wire was connected. Should we? Let's now use the initial charges. Let's say since the charge. Let's say, please look at this. Let's say since the charge in since the charges are equal, this is QB and this is QA. I'm checking. If I put the same charge here, divide, let me see what you have. If I put the same charge, is it the same thing we did when we started? That is before wire was connected.
It was the same charge.
Was it the same charge?
Yeah.
Before wire was connected.
You still give us back.
80,000 and 40,000.
Should we?
Yes.
Okay. I'm thinking of another way to prove it to you.
So I actually understand what you said.
Okay, you understand that one, should we?
Yes.
Because some person said I don't understand. So the voltage of A before will be the voltage of B after, because there will be equilibrium. And voltage of B will be the voltage of A after. So, but I believe this is physics. I should have other ways to look at it and explain. Okay. It's not working. It's not working.
Let's go to chemistry.
Okay, let's solve the last question then move to chemistry. It's not working. But I believe that should be what we have for now. But I believe once I find another way to explain it, I will definitely throw light on it in our next question. So let's calculate the final potential of each sphere. Okay, we've done it now.
So also the complete the charge transfer from one sphere to another.
Question was?
That's a question. What was the answer?
We've solved it now. Calculate the charge transferred from one sphere to the other in number D. And D is simply where we said that it will move from B to A now. Where we said that the charge will move from B to A when connected with wire. And charge in E will be equal. We said something like in equilibrium, the charges are equal. It will be evenly distributed. That's E now. E will be equilibrium. At equilibrium or connection with wire, what you have is equilibrium of charges. The charges will be distributed evenly. So that's your E. I think we explained that one with maths. So calculate the final potential. We've calculated it. The final potential we got QB. Wait, so have we calculated the final potential?
Yes.
No, I doubt. I think what we calculated is the final charge. Shall we see?
This is what this is it now.
Yeah.
That's the
Final, to calculate final potential, we should use the final charges to calculate the final potential.
yes, and that is what we did.
Where did we do it?
2 times 4 times 10 to the power.
This is charge now, QA.
Uh-huh.
This anything Q means charge.
Yes, I know. That's for QA now. That's for the first potential now.
Hey, God forbid, I will not be among of that. Among
Yes, now. 9 times 10 to the power of minus. 9 times 10 to the power of
20,000.
Okay, yes. I was looking at this. So this is VA, shall we?
Yes.
Thank you. So here is our VB.
VP is
Yeah, down there.
Okay. That means we answered the question before looking at the question. Wow. So we are done for today. So please, what it means is that our V before the wire connection is equals to VB when wire was connected after connection. So after connection, VA before equals to VB on connection. Then VB equals to VA after connection. So that means if this was 20 after connection, this is also 20. If this was 40 after connection, this is also 40. So we are correct. That's how to check it. So please, let's revise our chapter 2 chemistry and then we'll go home. We've tried today.